In this video, I'm going to show you how we can find the partial derivatives of functions. Find the first partial derivatives of these functions. The first function is f of x comma y is x to the y. Attention, these examples are not simple examples. These are a little challenging. Our function f has two variables, x and y. So basically, for this function, we have two partial derivatives. Partial derivative of f with respect to x, which we can use this notation, or simply we can use this notation. And partial derivative of f with respect to y, which we can show also with this notation. Both of these notations are the same. Before we start finding the partial derivative of this function with respect to x and then with respect to y, let me remind you some formulas from derivative. If you remember, when we had derivative of x to the p, which p is a number, like x to the 4 or x to the 5, derivative is with the power rule px to the p minus 1. We use this formula when the power is a number, like x to the 5, x to the 4, x to the 10. But sometimes we need this formula, which x is in the power, but the base is a number, like 2 to the x, 3 to the x, 10 to the x. And the derivative of b to the x is b to the x ln of b. For example, derivative of 5 to the x is 5 to the x ln of 5. Now that we remember these formulas, let's back to our question. First, we want to find the derivative of this function with respect to x. So x is the variable. And when we are finding the derivative of a function, the partial derivative of a function with respect to a variable, the other variables are constant. So here, y is like a number, like 2, 5. So which one of these two formulas we have to use for this case? The first formula, exactly. Because for us in this question, x is the variable, so x is the variable, and y is a number, like x to the 4. So for finding the derivative of x to the 4, we use this formula, the first formula that here we have. So partial derivative of x to the y with respect to x is y. We bring the power, because it's a number, down, and then we subtract the power by 1. Now, what about the partial derivative of f with respect to y? This time, x is a number for us because y is our variable. We want to find derivative, the change of this function with respect to y. So y is our variable, x is our number. So this is like 2 to the y, or 3 to the y, or 10 to the y, because x for us is a constant, y is our function. So this time we have to use this formula. And based on the formula that here we have, derivative of x to the y would be x to the y ln of x. Attention, x here plays the role of b. Derivative of b to the x is b to the x. So the derivative of x to the y is x to the y times by ln of b. b is the base, and the base is x. So ln of x. So these are the first partial derivative of this function. Let's move to the next example. The function r, which has variables p and q, is given by this equation, tangent inverse of p times q to the 3. Remember, derivative of tangent inverse of x is 1 over 1 plus x to the 2. Derivative of this is that. Now here we have tangent inverse of an expression. So we use same formula. We have two partial derivatives here. Partial derivative of r with respect to x, and partial derivative of r with respect to x not x with respect to p, and partial derivative of r with respect to q. For finding derivative of this function, first we notice we have tangent inverse, and we use this formula of 1 over 1 plus whatever is here, which is our x in this case. This expression plays the role of x to the 2. So 1 over 1 plus p q to the 3 all to the 2. But attention, we have to use the chain rule here because the pq to the 3 is inside of tangent inverse. So we have to multiply this answer by derivative of the inside. But derivative of inside, when we look at the inside, we notice that we have p and q. Here our focus is on p. We want to find partial derivative of r with respect to p. So find derivative of pq to the 3 with respect to p. When you want to find derivative of this with respect to p, this is a constant, this is a number. So just focus on p. Derivative of p, like derivative of x, is 1. So derivative of p is also 1 times by its coefficient. So derivative of pq to the 3 with respect to p is just q to the 3. So the final answer is q to the 3 all over 1 plus p to q to the 6. Now let's find the partial derivative of r with respect to q. Same method. Derivative of tangent inverse is 1 over 1 plus pq to the 3 all to the 2 times by, now we want to find the derivative of this with respect to q. And when you want to find the derivative of this with respect to q, p is just a number, so leave it. Derivative of q to the 3 is 3q to the 2 times by p. So derivative of the inside is 3pq to the 2. Which can be written as 3pq to the 2 all over 1 plus p2q to the 6. Attention, we can put a 1 here. Numerator multiplies by numerator, denominator by denominator, and we can simplify it as this. So the first partial derivatives of these functions are these two expressions that we got here. Now look at this strange function. The function is given as an integral. F is integral of t sine of e to the t dt from x to y. This function f has two variables, x and y. So basically, immediately we find that, okay, we have to find the derivative of f with respect to x and partial derivative of f with respect to y because it has two variables, as you can see here. Maybe you think also we have t, but attention, two things. First of all, based on whatever we have here, this function f has only two variables, x and y. The other thing that is more important even than this is that when you are finding this integral, at the end you have to plug in y and x in the answer of the integral. So the answer of this expression is not dependent to t. T is just a variable. This function at the end would be a function in terms of only x and y. So t goes away because we replace t at the end with y and x. So this function has only two variables, x and y. But how we can find the derivative, the partial derivative of this function? You have to remember the fundamental theorem of calculus for this question. Let me remind you briefly the fundamental theorem of calculus. It was something like this. When we have integral of a to x, a number, a is a number, 2, 4, anything, any number, to x of any function ft dt, if you want to find derivative of such expression, its derivative is very simple. Only plug in this inside the function and derivative of this expression is only f of x. So simply only plug in this expression. And let me add something to that. If this expression is not x, is something like 2x or x to the 2 or any other function, at the end here you have to multiply this by derivative of this also. But if it is only x or a simple variable, only thing that you have to do is derivative is just keep this function, whatever it is, replace t with x. What about this a? Because this a is a constant, we ignore it because its derivative is 0. This is fundamental theorem of calculus. Based on this, let me start with this. I want to find the partial derivative of f with respect to y first. Then I go back to partial derivative of f with respect to x. The reason that I want to start with this is that when we want to find the partial derivative of this function with respect to y, y is exactly upper bound of the integral, like the fundamental theorem of calculus. But if we want to find the partial derivative of f with respect to x, the problem is that the x is in the lower bound, so it's a bit more challenging finding partial derivative with respect to x, although it's not hard. Based on what I explained here, can you tell me what is partial derivative of f with respect to y? As I said here, simply look at the expression, forget dt, focus on the function. Replace every t with whatever is here. That's your derivative. And integral cancels completely. Look at the answer at the right side. You don't have any integral. So what is partial derivative of this function with respect to y? It's really, really simple. The answer is y sine of e to the y. This is the end of the story. What about partial derivative of f with respect to x? You cannot use fundamental theorem of calculus in its basic form, which is this, right away for finding partial derivative of this with respect to x, because your variable should be upper bound. So what should you do? You have two choices. You can remember the general version of fundamental theorem of calculus. The other way, which I recommend for this question, is to use a property of integral. If you remember, we can switch the upper bound and lower bound of any integral. So we can write this as an integral of y to x of t sine of et dt by putting just a negative outside. So whenever you have a definite integral like this, x to y, you can switch the two bounds. But when you switch lower bound and upper bound, don't forget to put the negative outside. These two are equal. Now, we can use the fundamental theorem of calculus because x is in the top. Now let's find the answer. For finding the partial derivative of f with respect to x, don't forget to put the negative which is here. Now focus on this. Based on the fundamental theorem of calculus, the derivative of this integral is simply plug in x for t. So the answer is negative x sine of e to the x. If you like, you can put the bracket, and that's it. This is the answer. As you can see, at first this question seems challenging, but the answer is really simple. Before I jump to the next question, let me add something to this question. Suppose the question, instead of being this, it's a little different. Let's suppose it's x to the 2 here. When you switch the two upper bound and lower bound, you get x to the 2 here. What would be the answer? What would be the partial derivative of f with respect to x if here we have x to the 2, not x? Then the answer would be negative x to the 2. You plug in this here, sine of e to the x to the 2 times by derivative of this. When it is x, because derivative of x is 1, you don't need to be worried for that. But when it's other than x, you have to multiply your answer by derivative of that, which in this case would be 2x. This is the answer. But for this question, it was not so complicated. And the answer is this. Let's move to our last example for this video. We are given function u as x to the y over z. The function u has basically three variables, x, y, and z. I know it didn't mention clearly which of these x, y, z are variable. Because it's not mentioned, we suppose all of them are variable. Maybe some of them are constant, but because it didn't mention anything, so we suppose all of these variables in the right side as variable. So it was better that we had u of x, y, z equals x to the y over z. Then it was more clear that these are variables. But anyway, it's given in this form. So for this function, we have three partial derivatives. Partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. When you want to find partial derivative of this expression with respect to x, y and z are constant. So this is similar to x to the power of 5 over 7, something like that, because x is the variable. How you find the derivative of this? Simply you are saying we bring the power down, so do the same thing here. So the partial derivative would be y over z times by x to the power of y over z minus 1. And that's it. This is the answer. Very simple. For finding partial derivative with respect to y and z, their story would be different, because this time the variable is in the exponent and we consider this as a constant, because here our focus is on y and y is in the power. So this would be different. You cannot use same formula. So for this case you have to use basically this formula. Derivative of b to the x is b to the x ln of b. So based on this formula, can you tell me what is the answer? The answer is x to the y over z. Repeat the function. Derivative of b to the x, b to the x. So derivative of x to the y over z is x to the y over z times by ln of the base, which is x. Is this a final answer? No. Wait a minute. In this formula, the power is simply x. And we know that always at the end, based on the chain rule, we have to multiply the derivative of inside, which is derivative of x, which is 1. But in this example, their power is not simply y. If it was y, derivative of y is 1. But it's y over z. What is derivative of y over z with respect to y? When you want to think about y over z, please attention. Focus on y and don't worry for z. Z is a number, so think it as y over 4. What is derivative of y over 4? 1 over 4, because it's a constant. So what is the derivative of y over 10? 1 over 10. So what is the derivative of y over z? You don't need to use any quotient rule or things like that. Derivative of y over z with respect to y is 1 over z. So at the end we have to multiply this 1 over z. And finally, what is partial derivative with respect to z or z? The partial derivative of u with respect to z would be, again, x to the y over z times by ln of x times by derivative of this. What is derivative of y over z with respect to z? This time you have to use quotient rule, because z is your variable, y is a number. This is like 4 over z. What is this derivative? You can move z to the top and write as 4z to the negative 1 and use power rule or use quotient rule. Derivative of this based on the power rule would be derivative of the top, which is 0 times the bottom is 0, minus derivative of the bottom, which is 1 times by 4, negative 4 over z to the 2. If the derivative of 4 over z is negative 4 over z to the 2, what would be derivative of y over z with respect to z? It would be negative y over z to the 2. This is the answer. I hope by watching this video, you have learned a little more about finding first partial derivatives of multivariable functions. These examples very little challenging, and if you want to learn more about partial derivatives, especially higher order partial derivatives, watch my other videos in this regard. Please subscribe in my channel and see you in the next videos.